All right, let's talk about the chain rule. It's one of the most important tools in calculus, and if you're doing any kind of differentiation with composite functions, functions inside other functions, you're gonna need it. So let's start with the big idea. Imagine you've got a function like f of g of x. That's a composite function. You're plugging x into g and then plugging the result of g into f. So x goes into g of x comes out, and then f takes that and gives you f of g of x. Now, if you want to know how fast f of g of x is changing with respect to x, you need to consider two things: how fast g is changing with respect to x, and how fast f is changing with respect to g. The chain rule tells you exactly how to do that. Here's the rule in plain English. The derivative of the outer function evaluated at the inner function times the derivative of the inner function. In symbols, if h of x equals f of g of x, then h prime of x equals f prime of g of x times g prime of x. That's the chain rule. Let's make this more intuitive. Think of x as going through a pipeline. First, it goes through g, then it goes through f. A small change in x causes a small change in g of x, and that causes a change in f. So if delta x is small, then delta g is approximately g prime of x times delta x. And then delta f is approximately f prime of g of x times delta g. Multiply those together and you get delta f is approximately f prime of g of x times g prime of x times delta x. That's why the derivative of f of g of x with respect to x is f prime of g of x times g prime of x. Now let's talk notation. In function notation, again, if h of x equals f of g of x, then h prime of x equals f prime of g of x times g prime of x. In Leibniz notation, if y equals f of u and u equals g of x, then dy dx equals dy du times du dx. It looks like you're canceling du's, and while that's not technically how it works, the structure reflects the dependencies. Y depends on u, and u depends on x. So when do you use the chain rule? Anytime you're differentiating a function that's nested. If you see something like 3x squared plus 1 to the fifth, or sine of x squared, or e to the x cubed, or ln of 2x plus 1, or root of x squared plus 4, that's a function inside another function. You need the chain rule. Let's go through a few examples to see it in action. First example, d dx of 3x squared minus 4x plus 5 to the eighth. The outer function is u to the eighth. The inner function is u equals 3x squared minus 4x plus 5. So the derivative is 8 times 3x squared minus 4x plus 5 to the seventh times the derivative of the inside, which is 6x minus 4. So the full derivative is 8 times 3x squared minus 4x plus 5 to the seventh times 6x minus 4. Second example, d dx of sine of x squared. Outer function is sine of u, inner function is u equals x squared. Derivative of sine of u is cosine of u, so we get cosine of x squared times the derivative of x squared, which is 2x. Final answer, 2x cosine of x squared. Third example, d dx of sine of x squared plus 1 to the third. This one has multiple layers. Let's break it down. Let a equal x squared plus 1, then b equals a cubed, then y equals sine of b. So dy db equals cosine of b, db dA equals 3a squared, dA dx equals 2x. Multiply them, dy dx equals cosine of x squared plus 1 to the third times 3x squared plus 1 squared times 2x. That's 6x times x squared plus 1 squared cosine of x squared plus 1 to the third. Now let's look at a different kind of application, implicit differentiation. Suppose you have x squared plus y squared equals 25. Differentiate both sides with respect to x. Derivative of x squared is 2x. Derivative of y squared is 2y dy dx, because y is a function of x. So you get 2x plus 2y dy dx equals 0. Solve for dy dx. Dy dx equals negative x over y. That's the chain rule at work. Another application, related rates. Suppose A equals pi r squared and r is changing with time. Then dA dt equals dA dr times dr dt. That's 2 pi r dr dt. Again, chain rule. Now let's go into multivariable calculus. Suppose z equals f of x, comma y, and x and y both depend on t. Then dz dt equals partial z, partial x, dx dt, plus partial z, partial y, dy dt. You're summing over the paths from t to z. Each path contributes a term. If you're working with vectors and Jacobians, the chain rule says the Jacobian of a composition is the product of the Jacobians. That's a more advanced version, but it's the same principle. Let's talk about common mistakes. First, forgetting to multiply by the derivative of the inner function. That's the classic error. For example, d dx of x squared plus 1 to the fifth is not just 5x squared plus 1 to the fourth. You need to multiply by 2x, so the correct answer is 10x times x squared plus 1 to the fourth. Second, misidentifying the layers. For example, sine squared of x means sine x squared, not sine of x squared. They're different. The derivative of sine x squared is 2 sine x times cosine x. The derivative of sine of x squared is 2x times cosine x. Third, using the chain rule when you also need the product rule. If you have something like x squared plus 1 to the third times e to the x, you need the product rule, and within that, the chain rule for x squared plus 1 to the third. Fourth, applying the chain rule at points where the function isn't differentiable. For example, if g of x equals 0 and f has a sharp corner at 0, then f of g of x might not be differentiable at that x. So to summarize, the chain rule is how you differentiate composite functions. The formula is f prime of g of x times g prime of x. Use it when you see a function inside another function. Break the function into layers, differentiate each layer, and multiply the derivatives. That's it. Now, if you want to practice, try differentiating these. 2x plus 1 to the fourth, cosine of 3x squared, ln of x cubed plus 1, and e to the sine x. Identify the inner and outer functions, apply the chain rule, and see what you get.